let's determine the convergence or divergence of this using the direct comparison test. So let's just go for the obvious, and this one's going to be a little frustrating but fun. So we're going to compare to, and let's just go for the obvious. Let's chop off that 6. That's kind of what we did in the last one. Chop off that constant. N from 1 to infinity of 1 over cube root of n, which, okay, now which, let's finish the sentence. Is this geometric? You might say yes, but you'd be wrong, sorry. It's easy to mix up geometric and p-series, like does the n go with the exponent or is the n the denominator? And well, in this case, the n is the denominator with an exponent of 1/3, so which is a p dash series that, converges or diverges? Diverges. Because p is equal to 1/3, and 1/3 is between 0 and 1. Okay? All right, now let's start comparing this to this and see which one is consistently bigger. So I'm switching colors yet again. It's fun. I like to put this one first. So because we have a series that is divergent, we would need to say that this is consistently bigger than the divergent series to say it diverges. If it doesn't, we have a problem. All right, let me try this again. Because we're going to compare it to this series, which is a p-series that diverges. Then in order to make any determination about it, well, we can't say anything about it converging, but if it's bigger than a divergent series, and let's go back to the first page of the notes. If it's larger than a divergent series, then it's also going to diverge. If the smaller one diverges, then the bigger one must also diverge. So I need that to be bigger. I really want that to be bigger, and we're about to find out if it is or not. So let's try this. 1 over cube root of n. I'm putting them in a different order this time because I really want this one to be bigger. You don't have to think about it this way, but I like to put the one that I want to be bigger over here. And so if I find that the comparison leads me to divergence, then I will put that one here. If it leads me to convergence, then I will put the one I was thinking up in my head on the right. That's just how I roll, what I like to do. Okay, which direction should we flip this flam-flam? Okay, this denominator is always going to be greater. Larger denominators make for smaller fractions, so this is going to be like that, consistently like that, actually no equal mark. So we have a problem. So this got us nowhere. So this is true for n greater than or equal to 1, so nothing can be determined. Now, before you get mad and stomp away, we have plenty of space left from this comparison. This comparison. Okay. All right, well, let's pick something else. Let's pick something else that we know. And I'm just going to go way out on a limb here because what I'm about to write looks nothing like this. So we're also going to compare it to something else. Compare it to this little guy right here, from 1 to infinity. This is a really good one that we can always go back to, and it is the harmonic series. 1 over n, and we know this one diverges. We found that it diverged in a different lesson in the integral test. So we're going to compare to this, which diverges. It's not geometric. It is technically a p-series, but yeah. Anyway, diverges. All right, so because it diverges, I'm going to pick, I want the bigger one. I got to word this just right. I want that to be bigger than a divergent series. So switching to blue again. So I want that to be bigger. So I'm going to put it over here on this side. So 1 over 6 plus cube root of n, and then 1 over n. And I really want this to be a less than or equal to symbol. So let's figure it out. So we're going to make sure it works. I'm actually going to go ahead and start writing it as a less than or equal to symbol. And I'm going to make sure it works. And if it doesn't, I'll be like, nope, 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 nope. Okay, so let's just start trucking. Less than or equal to. Let's keep solving. All right, something no one ever told you in Algebra 1, Math 1, whatever you took, 1. Lesson within a lesson right here. Once upon a time, I was solving for x. I had negative 2x less than or equal to 12. Your teacher said if you divide by a negative, you must turn that symbol around. And you were like, yeah. You also learned that if you multiply by a negative, you turn the symbol around. Or you also learned that if you change the order, like if I said 6 is greater than x, that's fantastic because x is less than 6. You have to turn the symbol around. There's another one. There is another one. And it's sneaky. If I reciprocate, I have to turn that symbol around. And it makes sense. There's that. All right, here's what I'm going to do. I'm going to move all the n's to one side, and it's not the most logical thing because you might look at that and say, whoa, I'm stuck. And yeah, fine. Move all your n's to one side. Don't necessarily have to move everything to one side as if we were factoring, but I'm going to do that. And then I'm just going to start thinking logically, what values of n will work? Let's pretend like it's calculator inactive, and let's just think logically. If I plug in a 1, is this going to work? Is this going to work? If I plug in a 1 minus cube root of 1, no. So 1's not going to work. 2 minus cube root of 2. Well, I don't know what the cube root of 2 is. Let's jump to a number that is cube rootable. Let's go to 8. 8 minus the cube root of 8, which is 2. Okay. Well, this works. If I have 8, and I'm switching colors here. We're going to go green for just a second. If I plugged an 8 in, just doodling over here, 8 minus cube root of 8, I would get greater than or equal to 6 because that's 8 minus 2. It's greater than or equal to 6. So yes, we have a true statement. And this is the threshold for it because this is 6 equal to 6. That is the threshold where it shifts. Lucky us. So n is greater than or equal to 8. Okay, well, I want this to be true for all n's greater than, let's go back to the first page, greater than or equal to 1 for all n, but I'm dealing with n's that are equal to 1 and up, right? So does it fall apart again? No, actually, this is going to work. So here goes. 1 over n is less than or equal to 1 over 6 plus cube root of n. That is a true statement for n greater than or equal to 8. Well, okay, now how is that okay if I wanted to start at 1? Because there is this is fun, because, I'm not going to write it, but there is a finite sum between 1 and 8, so we know that we already have that portion restricted. Because this is true, therefore, the series that they gave us also diverges. It has to also diverge. And again, here's why. We have a series that is consistently larger once you get past a certain threshold. And it's okay that that's not a 1 because nothing crazy or infinite happens between 1 and 8. And even if it did, actually, it would be okay because they're going to diverge anyway.